Hello, I'm Morris Fan, the professor of industrial engineering and management from Taipei Tech. It is my privilege to serve as a keynote speaker and presented to the ninth Big Data conference on Jeju Island of South Korea. I also thank Professor Cho's invitation. Today, I would like to briefly introduce my recent research that is assisted intelligence in Taiwan semiconductor practice. Actually, all the content I present today is based upon a real data project. So this is the agenda I would like to follow today. First of all, I would like to give a very quick introduction about the artificial intelligence and machine learning. And so then followed by the introduction of assisted intelligence. Then one of my IEEE transaction paper going to be presented. That is a case study of the artificial intelligence in semiconductor manufacturing in Taiwan. Then I conclude my research and give you some related research references. And then actually this is the online and the pre-recording. So for any question or comment, all the comments are more than welcome. You can send those to my email address. Okay, artificial intelligence is an area of computer science. Actually, it is a machine try to resemble the human's intelligence that emphasizes the creation of intelligent machines that can work for human being and act like a human, and finally can provide any insightful action or the knowledge and actually can do the assignment that is just so hard. There's really effort-taking or repetitive works for human beings. So machine learning basically it is a subset of artificial intelligence, and the deep learning also a subset of the machine learning. So how we experience machine learning during our daily life. So yeah, basically the machine learning is a method of data analysis that automates analytic model building. So this is we just filter or do the feature selection, the feature extraction or feature creation. Then we can build a model, then use algorithm that iteratively learn it from data. So how we experience the machine learning during our daily life. So there's some example like a website recommending items and speech and face recognition such as immigration office and security and customs. And in government agencies such as public safety, the CCTV cameras like a surveillance camera, the smart traffic flow solution by using the YOLO for social politics. And in the application of financial engineering and the banks and the other business in financial industry for two major purposes. For example, such as ATM services and in order to prevent the tax fraud or money laundering. So machine learning basically can be classified into two categories. First one is supervised learning, that is the data is labeled. So algorithms are trained using the annotated examples such as input where the desired output is already known. Then the COVID, the pandemic, infected is known as the positive, non-infected is known as the negative. And the second one, the unsupervised learning, is used against the data that doesn't have historical label. That means this is due to the amount way over to be handled by human beings. Then the system is not told the right answer in advance, those information from the website. So algorithm must figure out what is being shown. Then the goal is to explore the data and find some structure within. We've been using for a long time, like a clustering algorithm or test or TSNE for data visualization. And in between, there's another subcategory. It's known as the semi-supervised learning. It's used for the same application as well as the supervised learning, but it uses both labeled and unlabeled data for training. So some semi-supervised learning application in real life in the web pages classification. Why? It is way too many. So those items cannot be annotated by human one by one. So we only annotate a partial portion of all the items and use a pseudo label and by machine learning algorithm to perform the data annotation for human beings. And one of the hardest topic going to be reinforced learning. This is totally different one. This is known as non-supervised as well. With reinforced learning, the algorithm discovers through the trial and error which action yield the greatest or the best the possibly best rewards. So we have a big table. So what is plus, what is a negative? If you do something right, I give you the positive point. If you do something wrong in the wrong direction, I go into negative points. So so what reinforced learning is useful typically for the current application is on gaming and robotics. So based upon the algorithmic development, there are several steps. Initially, we have a DQ network and the policy gradient. Recently, there's a DDPG. This is quite well known and widely accepted. This deterministic policy gradient. And in 2017, this is the most recent methodology in reinforced learning that was developed by the OpenAI, and the proximal policy optimization uses the trust region to do the approximation of the policy distribution. This is based upon the sampling distribution. Okay, I consolidate the algorithm group by the learning style. Machine learning algorithms are categorized by the level of assistance they provide. Can get from the human, then how they change over time. So number one, supervised, we have a pre-labeled data and regression analysis. Unsupervised learning, no labeled data is available, like clustering. The third one, reinforced learning, like Q-learning. So actually, the reinforced learning is used for very stochastic or very uncertain environment, how the system can adapt to the uncertainty in the environment. So this is always the slide I like to talk about reinforced learning most in my class. The simple example of a child sorting Lego blocks illustrate the difference between 3 different machine learning styles. First, a supervised learning. Child has to sort the color blocks by matching the color of the block with the color of the bag. So I give some hint, I give the label, I give you the shape. And unsupervised learning, child has to sort the block by color by themselves, by shape or both, or without any further or prior instruction. So reinforced learning, child gets the feedback from mom when he does something right. I give you some reward. If you do something wrong, I'm going to teach you again, like a Chinese always teach children how to use the chopstick on the table. So where are we now? There's 3 types of artificial intelligence. First one, so we are doing now, we are trying for this artificial narrow intelligence. So there's some milestone like a Siri, Alexa, and Cortana. Then we moving forward. Now we are striving for to move forward to the next stage. That is artificial general intelligence. So refer to a computer that is as smart as a human being. Then the utopia going to be the artificial super intelligence. So that is an interact that is much smarter than the best human brains in practicality. So I think we can envision artificial super intelligence is coming maybe in the following 10 years. Then there's another categorization of the intelligence by TWC back in 2016 or around. So today I'm going to address only one, that is assisted intelligence. So this is a 4 type of intelligence. So horizontal axis represent the human. Does human being intervene in the system or not? The vertical axis, that means this is adaptability, more adaptability or not. Is a hardware or is it more adaptive? So look at the assisted intelligence here. So which is AI system that assists human beings in making decisions or taking actions. The hardware system that do not learn from their interaction. That means the human in the system. However, the machine learning can help people solve over 60 or 70% of the task. However, when they cannot handle that, the people going to intervene and to solve the problem. So, however, in this scenario, the human being and the machine learning or artificial intelligence, they do not interact with each other. Then learning from different type of data. We talk about data since typically there's three major model building philosophy. First one is domain-centric modeling, and model-centric modeling technique, and the data-centric modeling techniques. So we have several different types of data we need to face, like a text and natural language, like NLP, natural language processing, audio, the text-to-speech, the speech-to-text, and sensor data. Like we use the LSTM to deal with sensor data. The video with the video search, the pattern recognition. So the video and can transform into the image, and the motion traction, and for the security purposes, the image CNN is the most active, the research field nowadays, like image search, facial recognition, and the object classification. So yeah, a rich source of unstructured data is available and abundant in our daily life is fueling the rise of machine learning to understand the data better and further. So for the data lens, many types of data can be used to develop and train an AI. So we have a structured data like we have been studying when like a 20 year or 25 years ago, like a ER model or EER model, a relational database. And then semi-structured label or organized data with no guarantee of the data model consistency. Like a JSON, XML. JSON is a JavaScript object notation. And unstructured, like we use or we encounter in the social media every day. Information has no defined schema or structure, like a raw text, image, audio, video, and sensor data. So technology lens of AI layer. So we have 4 different layers: sensory layer, then we have a sensor, we construct a behavior layer. Behavior layer, we just extract those features for model building. Cognitive layer, use a different reasoning, a method or algorithm, deep learning. Finally, the foundation layer to apply to specific application domain, like use statistics, econometrics, optimization, complexity theory, computer science, and game theory. Okay, so machine learning take the raw data raw data to turn into the smart data. In between, we'd like to turn into, so we're going to screen out those features to learn the features that make up the model of the real world and make the prediction, make the prognostic, and finally to help people make decisions. So the raw data feature model deploy in production, finally do the prediction. And then we need to feed back to the raw data once again. We're going to evaluate ourselves if the data collected is good enough, with a good quality enough, or the number of the raw data is sufficient large enough. Then I will move forward to my today's focus. Is the case study. This is assistive intelligence that was already published in the IEEE transaction on automation, science, and engineering, October 2020. Is a data-driven approach for fault detection and diagnostic in semiconductor manufacturing. So all the data are realistic based upon the real data from the 12-inch wafer fabrication plant that is located in Jeju Science Park. Then the thin film. This is a thin film data set. It's known as a chemical vapor deposition, known as CVD. There's raw trace data. So that the processing step consists of the chamber A and chamber B. So we like to just depose a thin film on the surface of the wafer. A sample are totally imbalanced. That means things are due to really high yield, like over 98%. So the yield rate. So the sample are highly imbalanced. That means defective wafer is quite limited. So each wafer records different finish time. Like this one, first wafer with 315.3 seconds. For example, wafer 2 we have 370.7 seconds. So we have different the processing length. Likewise, for each wafer they have a different number of measurement. Like first wafer we have 310 pieces of the data, the measurement data. And for the wafer 2, we have 312 pieces of data. So we need to do the synchronization for each wafer, for the length, for the number of the measurement. So those details already mentioned in the paper. If you feel interested, I can send my sample paper to you for your perusal. So the idea is this abundant feature. So the engineer would like to screen out a smaller set of the key feature among abundant number of features. So to help them to perform the fault detection task every day. So so this is the framework of the research. Input the road trace data. You can see that first step, identify key parameter among abundant. And then based upon the identified key parameter, they also like to identify what is the key processing step. Since the processing time is quite long, it's like 320 seconds. They access our research. Can you pinpoint the specific timing for that particular item? Then for the practical point of view, engineering going to focus on that particular item, particular processing time, and construct the SPC, statistical process control, for monitoring. That's it. That's good enough for monitoring for detection. So if we could do so, engineers do not spend too many SPC chart, too many statistics for monitoring. This kind of tedious, this kind of time-consuming work. Then third one, so if we identify those key parameter and key processing step, so can we do the validations? Is that really can separate the good wafer and the bad wafer? In step 3, we like to use machine learning for classification and to validate the key processing time and key processing step, the key parameter and the key processing step identified. They do justice. Then finally, based upon the research outcome review, and we found, and can you just present in the dashboard? So the step 4 is in relation to the data visualization. Then we have a full set about the fault detection classification system. For the key parameter identification, so this is a label definition. So there's only 2 labels, they dichotomous. So define the label on time series road trace data. So originally we have a 66, so we just exclude 7 qualitative SVID. SVID, that's a parameter, that status variable identification variable. So now the remaining going to be the 59 SVIDs. So this is illustration. So for each one, going to represent a particular parameter for each wafer, of each wafer. So like a good, and then bad. So then we define the label. Since for each wafer, the time elapsed is 315. So for each second, the good label has been attached for a good wafer. A bad label has been attached each measurement of every time step to the bad wafer, like the illustration does. Then we actually we try abundant different machine learning methods. So finally we select the random forest. It's quite robust, which was designed and proposed by the Leo Breiman, the UC Berkeley in the year 2000. It's a wrapper method for feature selection. Wrapper, that means when the model building and the feature selection can be done simultaneously. And trace data do not need to normalize or standardize in advance since this is an aggregation based approach. And the objective function we use in CART, we use the gene importance. So how many trees we use? We use 100 trees that use as experts. The maximum depth for each tree, 7. The maximum feature, this is 8 out of the 59. Then this illustration calculates the importance rate of each parameter. You can see that. So this is the red line represents chamber A, the blue line represents chamber B. So these two lines resemble each other. They provide the similar information. They parallel each other. So you can see that around here with really a comparatively high importance. That might be the key parameters. Then we use the k-mean since key or non-key. So we use a k to do the clustering. Then you can separate the 15. Totally, we have a 59 SVID. So separate into 2 groups. So you can see that on the left side, this is chamber A, this is chamber B. The 16 key parameters from chamber A, and the 17 key parameters screened from the chamber B. So we select a certain key SVID, and then so we have an answer. We check with the engineer's domain. All the key parameters are found. So the key parameter concur by the engineer's domain, including from the SVID from the 25 to 32. So actually will provide a systematic approach to the process engineering. In the future, you don't have to collect so many historical data or domain experiences. During the pilot plan, you just input those data into the proposed methodology, then you can identify the potential key parameters. So there's one thing I would like to point out, the SVID 12. So we do the validation, the SVID 12 is another key parameter. The domain engineer never pay attention to finally, which was confirmed by the domain engineer. So this additional insightful knowledge can be provided by the proposed methodology. And now we have a key parameter. Now, how about the key processing step? So based upon those identified key parameters, so we just collect the corresponding the time. That's a key step. This is intervals of the processing time. So for the chamber A, from the first second one to second the second 315 for chamber A. For chamber B, the second one until the second 309. So those processing steps were defined by process engineer. So based upon the definition, we try to where for the chamber A and chamber B, where's the key process step we should focus on. So for the label definition, so now in the previous stage, we identified key parameters. So those features are going to be the key feature. Now we would like to identify the key processing step, that's key processing time. So the time going to be the feature we like to screen out. So the parameter, so we just do the transpose of the data matrix, do the transpose, so time going to be the feature we like to screen out. So we have a 59 matrices since corresponding to the 59 SVIDs. Then we also use a random forest. You can see that for chamber A, chamber B. This is a key processing step 7, key processing step 11. This is a key processing step 5 and a key processing step. This is the processing 7 with a higher importance from chamber A and chamber B. So from here, it seems we found the corresponding key processing step 7, which is quite have an influential impact on the process. So now do the mapping. So for the key SVID 25, you can see the little discrepancy that might be the problem occurs. Then for another key per SVID 2028, the processing step 7, processing step 11 with a higher importance. For chamber B, this is a processing step 2. It was a higher importance. So we can see that the SVID, we see the profile of the SVID 28. You can see the discrepancy. So now we have something in our mind. In the future, we might only focus on the step 2 and the step 7 and construct the SBC for fault detection, and that is done. So we have this outcome. Then the project almost finished. Then, however, the top management also asks the research team like to do some data visualization. That is additional aid to the fault detection and classification team. So we use a TISNI. TISNI is a visualization tool that can handle the multivariate parameters. So now we screen out 9 parameters. So for each parameter, which corresponding to 315 seconds, so 9 by 357, which corresponding to for chamber A, this is 2,835 features corresponding to chamber A, and the 2,781 feature for the chamber B. So all the dimension need to be reduced into a 2-dimensional space. So we use the TISNI, the parameter perplexity 30, exaggeration, 4 learning rate, 500 iteration, 1000 were used. So you can see we do the comparison. Yeah, you can see that the PCA, principal component analysis. Yeah, this is very difficult to differentiate the good wafer and bad wafer, especially for chamber A. However, for the TISNI, you can clearly separate the good wafer. This is a good wafer in blue and bad wafer in bad, like this. So correspondingly, this is corresponding to. Yeah, this is the bad wafer. There's a bad wafer here, corresponding to the steps number 7, processing step. Okay, I stop here. This is only one example of the system intelligence. So in 2019, we also used Fourier transform and some machine learning non-parametric method to perform the key parameter identification using the image processing step published in the IEEE transaction in semiconductor manufacturing. So there's another paper about the semiconductor run-to-run control, and which is use the EWMA controller to address a high-mix product, also published in IEEE transaction, automation science and engineering. This is another important, this is all just published yet, resolve the problem between the back end of line and the front end of line problem. This has never been solved in the semiconductor practice or semiconductor literature before. Then there's another paper just to appear in the IEEE transaction on automation science and engineering. This is TFT LCD. We performed the product to product virtual metrology task by using the transfer learning. So this is performed the automatic defect detection without using the manual annotation using the cycle gain. So this is another paper. It's almost accepted by IEEE. We use a SOM, cell organizing map, and the ADA boost to identify the wafer to wafer variation in semiconductor manufacturing. There's a no defective information provided, so we'll try to differentiate those regular or normal wafer, what is the variation between them. Okay, I stop here. Thanks for your listening. Your comment and your criticism and the suggestion are more than welcome. Present to my email address. I really looking forward to the future collaboration with you guys, with an old friend from South Korea. Thank you.